In progress. All right. So the introduction. So matter at interfaces usually has different characteristics from that in the bulk of the media. And as a consequence, a study of interfaces has been developed. So what this means is my screen has gone. What happened? Sorry guys. I'm not tech savvy. So what this statement means is that, okay, so when matter is in bulk of the media, it has different characteristics from when it's outside of the media. That's basically what that sentence means. Like when matter is in air and then it moves through and then it goes to water, the characteristics of matter when it's in water is different from when it's in air in general. So I don't want to read all these sentences. So the subsequent behavior of these formulations in vivo is governed by interfacial process. In vivo, as we know, is within the living. So interfaces are categorized according to the phases that they separate. So there's liquid-liquid interface, which separates liquids from liquids, then liquid vapor, which separates liquid from vapor, solid vapor, which separates solid from vapor, and solid liquid. So I'll start with liquid interfaces. So for a single component liquid, that means like a liquid which has one major component. The molecules in the liquid are subject to attractive forces from adjacent molecules. Let me use water as an example. So water is a single component liquid. So the molecules within water, they're subjected to attractive forces from the molecules within itself. Like water has molecules which are next to each other, and then there's forces it subjects to itself. So in the bulk of the liquid, the molecule are subjected to equal attraction in all directions. So water itself as a liquid, inside the water, all the molecules, they have equal attraction in all directions. This is what I mean. So in all directions, the attraction is the same. But at the surface, which is over here, the net attractive force is towards inward. Oh, wait. This net inward attraction reduces the number of molecules at the surface. So within the bulk, which is probably over here, the forces will be equal. But at the surface, which is over here, the attractive forces will be going downwards, which means it's trying to reduce the surface tension over here. So this results in different characteristics at the surface from the bulk, which gives rise to surface tension and surface free energy. So if we have equal forces within this part, which puts the molecules at equal distances and they keep moving, and then over here the forces are different and it moves the water molecules downwards, it means there are going to be different characteristics at the surface and different characteristics at the bulk. That's what gives rise to surface tension. So an example given as per these notes, parallel wires joined at the top. So this is one wire and this is the other wire. So it's joined at the top over here. So if there's a slider, this is the slider. The slider is named M1. So if you attach a weight to this slider, which is this weight M2, it holds the slider in position. So if a film soap solution is formed between the upper wire and the slider, so like I said, the upper wire is the one that is joining the parallel wires, and there's a slider over here. So the one that is colored gray, this is the film soap solution that is formed. So if you have film soap solution formed between the upper wire and the slider, the film will rapidly contract because of the surface tension forces. Like we've said, surface tension at the surface, the forces move downwards. So there's gonna be some some bit of contraction, which is gonna lead, there's gonna be contraction because of the surface tension forces. So if you introduce a weight M2 to the slider, it will help this slider remain in what? In equilibrium, which means the even if it expands or contracts, there's not gonna be a change in the surface. Why? Because the surface will not expand or contract, it will remain the same because the weight has held the wire in the slider in the same position. So surface tension depends on the nature of interfaces and their lengths. So two interfaces, in this case, the interfaces, there's this one interface and this other interface. So surface tension depends on the nature of the interfaces and their length. Two interfaces means the length of the film air interface is 2L. This is down here. Let me just scroll. Here. The surface tension is therefore independent of the area of the film, but depends on the chemical nature of the interfaces and their lengths. That's what I mean. There's an interface where there is air, and there's an interface where there's a soap film. Those are two different interfaces. However, the surface tension is not dependent on the area of the film. What it depends on is the chemical nature of the interfaces. So the chemical nature of the soap film and the chemical nature of air are what is gonna affect the surface tension in this case. Are you with me up to there? Are you understanding? Or is there a part where I have lost you? No answer. What does that mean? Nanielewa?
Tuko pamoja.
Pamoja. Okay, sawa. So, what I was saying, the surface tension depends on the nature of surfaces and their lengths. The surface tension is independent of the area of the film. So the area of the film is the one that I'm saying is the soap film. It does not affect the surface tension. What affects the surface tension is the characteristic of the film, the characteristic of the air, and the total length of the film air interface. So because there is two interfaces, the formula is gonna be 2L. So surface tension is usually considered as the force acting parallel to the surface at right angles to a line of 1 meter length anywhere in the surface. This is a very long definition. I think it's MCQs, so I'm not sure that I want to focus on definitions. So in the example given above, the surface tension is annotated by this strange looking Y. So it's the force acting perpendicular to the surface. Perpendicular from primary school, we know it's 90 degrees. So the formula is this one. So I went to the internet. Let me give you first the definition I found for surface tension in the internet. So surface tension is the property of the surface of a liquid that allows it to resist an external change due to the cohesive nature of its molecules. So basically, let's assume like we go back to water. So water has cohesive molecules. So the stronger, if the cohesive molecules of water are stronger, it means it can resist external change, which means the surface can't be broken easily. Ideally, that's what surface tension means. Like the surface of the liquid doesn't allow it to be moved or to go inward, to contract or expand, because the molecules within the bulk is more strong. So ideally, the primary formula I'm getting for surface tension on the internet was Y is equals to F over 2L. So F is the force, obviously. 2L is what I've given the length of the two interfaces. So this is also shown in this formula. So per the diagram above, there's the mass 1. The mass 1 is the slider itself. Let me just go back up. Mass 1 is the slider. It has its own weight, which exerts a force. Then mass 2 is the weight that is put on the slider to put it stationary. That way it doesn't expand or contract. And then into brackets G over 2L. 2L is the length of the two interfaces. So surface tension, if you are calculating using that diagram, you're going to input this one. So surface tension is equals to mass 1 plus mass 2 multiplied by, make it in grams, over 2L, which is also equal to F over 2L. So in case in a formula you're given different values, you're able to equate it to this formula. So G is the acceleration due to gravity. I don't know the acceleration due to gravity. Can anyone remind me the acceleration due to gravity? What was the value? Was it 0.8? I'm not sure. If anyone knows, you can inform us or write in the chat. So if the slider is moved a distance of X, expanding the film, the increase in total surface area will be 2Lx, as there are two surfaces, the front and the back of the film. This is just me explaining why there is 2L. So work done is hence Fx, and therefore surface free energy is defined as the work required to increase the surface area by 1 meter squared with unit. It's such a long explanation. I don't think it's important, but yeah. I think that formula is just showing trying to equate surface tension and surface free energy. That whole big explanation. Because ideally F is the force exerted, 2L is the length, the length of the between the two interfaces. So if you move the whatever, if the work done is defined by X, you multiply this original formula of surface tension is equals to F over 2L by X by X. So you have Fx over 2Lx is equals to F over 2L, which is also equal to the surface tension. So this is the surface free energy. This is the surface tension. And per this formula, it shows they are dimensionally equivalent, which means they'll probably be equal. They should be equal when you do your calculations. So yeah. So thereafter, let me take you to pressure difference across curved interfaces. So a pressure difference exists across curved surfaces to balance the influence of surface tension. So what we take into consideration is a bubble of vapor in a liquid. So usually a bubble, think of what bubble, a soap bubble, it should be spherical in shape. That is how it is normally when there's no force exerted either from the top, from the bottom, or the sides. So the bubble remains in spherical shape. It remains the same size because the surface tension forces are balanced by internal excess pressure. So the formula for the excess pressure is given by change in P is equals to 2 multiplied by the surface tension over R, where R is the radius of the bubble, because we've said it's a sphere, and sphere, it has radius. So that is for a spherical surface. Are you getting, guys? Are you with me? Hello?
Yes.
Okay, sawa. So if you have non-spherical surface, they're described by two radius of curvature. So the equation becomes the change in pressure is equals to surface tension of over into brackets 1 over R1 plus 1 over R2. So what I got from this was non-spherical surfaces, they usually have two radiuses, and then the two radiuses are both gonna influence the excess pressure. So that's why they're both included in the formula. And this is known as the Laplace equation. So over here, like this definition was rather long. So I went and researched on something called the Laplace law. So what it states is that the pressure inside an inflated elastic container with a curved surface, for example, a bubble, is inversely proportional to the radius, as long as the surface tension is presumed to change a little bit. So when you have your bubble over here, so the pressure inside the bubble is inversely proportional to the radius. That's why in the formula, it's 1 over R1 plus 1 over R2. So as long as we are assuming that the surface tension will change a little bit. So we're assuming the change in pressure will also come with a change in surface tension. Yeah, that is the Laplace law. Unfortunately, you just have to shika it like that. Like pressure inside a container or with a curved surface, for example, think of a bubble, the pressure is inversely proportional to the radius, as long as we are presuming that the surface tension is changing a little bit. Even that last part, you don't have to shika it. You can just shika that the pressure inside the bubble is inversely proportional to the radius. Yeah. So after that, there's the influence of temperature. Influence of temperature to surface tension, that is. So many liquids, if there's an increase in temperature, it leads to a decrease in surface tension. And the decrease in surface tension with temperature is approximately linear. So if you had a graph and then there's an x-axis and y-axis, the line is moving, is it diagonally? It's gonna be like a straight line, not a curved line or anything. So as the temperature approaches critical temperature for a liquid, the intermolecular cohesion forces approach zero. So basically, what I thought about this was like the Brownian motion. Like when you hit a liquid, the molecules within the liquid, they move so much. So when they move so much, it means the pressure, the cohesion forces in between these molecules are really being broken down, and the molecules are moving about a lot. And that means that there's gonna be a decrease in the surface tension, because the surface tension is dependent on the cohesive forces inside the bulk itself, as well as the forces at the surface. So if you're disturbing the bulk and the cohesive forces, it means that your surface tension is also gonna be affected. Think of like a balloon. So inside the balloon, there are molecules, yeah? And the bulk inside the balloon is air, yeah. And then assume surface tension is acting on the surface on the balloon itself, like the plastic holding the air inside. So when you hit the balloon, it's the molecules are gonna keep moving faster and faster. That means you're affecting the cohesive forces, and eventually the balloon is gonna burst. That means that the surface tension has been really reduced. So the only exceptions to this are some molten molecules. I did not have time to search for such molecules. So the interfacial tension between two immiscible liquids arises as a result of imbalance of forces in an identical manner to the surface tension between a liquid and its vapor. Interfacial tensions generally lie between the surface tensions of the two liquids under consideration. So for the spreading coefficients, I sent a link to the group that I found a bit easier to use to explain. Wait, let me ask, can I project the link that I sent to the group, the people who have been projecting? Is it possible?
Yeah.
Okay, so I have to stop sharing this and then go to there and share the link. Emma?
Yeah. Just open the link.
Okay, can someone do that for me? Because this laptop is a bit on the slower side.
Is it on WhatsApp hapa?
Yeah, I sent it on WhatsApp. I sent it to the WhatsApp group. So do I stop sharing and then someone can project it for me? Because it will be easier and faster. Kindly, if anyone has opened it.
Let me project. Amasaru, you've managed.
No, I've not been able to find it.
I actually projecting in a few seconds. There it is.
Okay, sorry for the background noise. I don't know what is being built in my background. So let me start by defining for you guys spreading coefficient. So basically, spreading coefficient is the measure of the weighting behavior. It's not in this representation bias. So I'm just reading to you guys the simple definition I found. So spreading coefficient is the measure of the weighting behavior of a liquid on a solid surface, basically. So if you have like a liquid which you pour it on a solid surface, how much the liquid wets the surface is the spreading coefficient. Another explanation is that the spreading coefficient is the difference between the interfacial free energy of a liquid-solid interface and the sum of the interfacial free energies of the liquid vapor and solid vapor interfaces. Okay, so from this slide share, I found it easy. So when oleic acid is dropped in water, it immediately spreads on the surface of the water. So the spreading liquid is oleic acid, and then the water is the sublayer liquid. So it's the liquid among which the oleic acid is gonna have a spreading coefficient. So generally, spreading will occur when adhesive forces is more than the cohesive forces. From your basic science, just scroll down. Adhesive forces are the forces which are within the liquid. Adhesive forces are the forces between the liquid and the surface which it is being spread on. So it's adhesive forces are the forces between two different molecules. And then cohesive forces, I'll go back to the example of water. The water to water molecules, they have cohesive molecules. So cohesive molecules are the forces that bring similar molecules together. So in order to have a spreading effect, the adhesive forces need to be stronger than the cohesive forces, which in this example, oleic acid should have stronger attraction towards part of the water molecules. So which will mean the cohesive forces between the oleic acid should be weaker compared to the forces between oleic acid and the water. And also the vice versa is true. The adhesive forces in the water molecules should be weaker than the cohesive molecules. So this one was an example of cohesion. Explaining it in physical pharmaceutics is a bit difficult, but I will try. So let's assume this liquid together over here is the water or oleic acid. So work of cohesion may be defined as the surface free energy increased by separating a column of pure liquid into two halves. So the pure liquid, let's say, is the oleic acid. If you separate it into two halves, that is the work of cohesion. And then scroll down so that I can explain the work of addition. So the work of addition may be defined as the surface free energy increased by separating a column of two immiscible liquids at its boundary into two sections. So the oleic acid, when it's spread into water, so the L, and let's assume L is the oleic acid, S is water. So they're immiscible. So when you separate them differently, that is the work of addition. So then you'll have the first immiscible liquid will be the oleic acid, which is the L at the top, and then the S would be the water. That is the basic definitions of the work of addition and the work of cohesion. So where the work of addition is stronger than the work of cohesion is where you're going to have the spreading coefficients. Yeah. So the spreading coefficient is the difference between work of addition and work of cohesion. And this long formula is what explains that. So work of addition is WA minus work of cohesion, which is WC, is equals to surface tension L plus surface tension S minus YLS, where L would be the oleic acid, S would be the water, and then minus YLS will be the surface tension multiplied by the oleic acid times the water minus 2 surface tension L, because again, there's two interfaces. It's such a long formula, but it's written over there. It's simplified. So what I was saying, keep scrolling. The spreading occurs when the spreading coefficient S is positive. So where the spreading coefficient is negative, it means the spreading liquid will form globules or floating lengths. This means the liquid, in this case, the oleic acid, which we put on top of the water, it means the cohesive forces were strong enough to resist, were stronger than the adhesive forces, which means the spheres were not interrupted, so they settle on top of the liquid. Like now you'll see the bubbles forming because its integrity has not been affected. But where the coefficient is positive, it means the adhesive forces overpowered the cohesive forces, which means they will mix a little bit. Okay, then scroll some more. When free energy of the spreading liquid and the interfacial tension with the sublayer is less than that of the sublayer, the spreading becomes spontaneous in an attempt to reduce a free energy sublayer. There may be saturation of the liquid with the other, and there may be change in the surface tension of the sublayer liquid. So basically, this is trying to explain where, if, for example, the oleic acid, when you spread it over the water, if at first the adhesive forces overpower the cohesive forces, then there's gonna be spreading, yeah? But once they assume the water has a limited amount of capacity, let's say the oleic acid is 5 and the oleic acid is 10 and the water is at 5. So when the oleic acid 5 molecules combined with 5 molecules of water, it means the water becomes saturated. So in that case, there's going to be a phenomena where it was at first the spreading coefficient was positive, and then it becomes negative after saturation, which means the spreading liquid, it will coalesce and form a lens on the surface of the sublayer. Are you getting? Are you guys getting? Is it making sense?
Yes.
Yeah, it's making sense.
Okay. So in the case of a duplex film, if S becomes negative after saturation, it forms a monolayer and excess liquid remains as a lens on the surface. So basically there's gonna be a bit of spreading and then there's still gonna be a bit of the liquid that retains its integrity, and then it's gonna be in a lens shape. So scroll a bit low. Fatty acids and alcohol have a high spreading coefficient. Non-polar chain length, as the non-polar chain length increases in an acid or alcohol, the spreading coefficient will decrease. This is what we are talking about. It starts decreasing and then it becomes saturated. Then propionic acid and ethyl alcohol have high spreading coefficient, which means the adhesive forces will outpower the cohesive forces. And then liquid petroleum does not spread on water, which means it has very strong cohesive forces. So these are the applications of spreading coefficients: absorption of medicament from creams, lotions, stabilization of emulsions, and coating of tablets. Yeah. You can stop sharing so that I can go back to now sharing the slides. You can see. Can you guys see?
Yeah.
Okay, so yeah, basically that presentation was just explaining all of this in simpler terms. See this, in practice, when two immiscible liquids are placed in a contact, the bulk liquids will eventually become saturated. This will change the values of the various surface and interfacial tensions. So there's an initial spreading coefficient, which is an immediate value, and a final spreading coefficient after saturation has taken place. That's what I meant. So examples of things which undergo that, there's benzene and hexanol on water. So there's initial spreading because the coefficients are positive, and then when saturation has occurred, there is gonna be negative spreading coefficient. So then it's gonna, that means it's gonna spread immediately, and then after it stops, it's gonna leave a monocular layer of benzene. So capillary rise and tension meters. So we've reached.
Carol,
Yeah.
before you continue, when you say, been seeing they say when they become saturated, what they become saturated with each other, like the benzene becomes saturated with water and water with benzene,
Yeah.
or
Yeah, because it's a mutual saturation.
oh, okay, thank you.
Yeah, so both of them have been saturated, so they can't absorb each other. So it means now for both of the liquids, the cohesive forces now become stronger than the adhesive forces. So then there's gonna be that initial layer that is there, and then now there's also gonna be formation of lenses, flash lenses. Is that okay?
Yeah.
So capillary rise and tension meters. So these are ways to measure surface and interfacial tension. So the first one is the capillary rise method. So usually it's considered to be the most accurate way to measure surface tension. Since the surface of the liquid is undisturbed during the measurement, the time effects can also be followed. Capillary tubes, I think we've seen them in the labs. They're really tiny. So I'm assuming if you put it through a liquid, it does not interrupt the surface tension. So the capillary tube is placed in a liquid, provided the angle of contact is 90 degrees. It's a right angle. So that means if you put it at the correct angle, the liquid would rise in the tube to a certain height. So this was the original one, and then the capillary tube was inserted. After you inserted the liquid here, it moves to a certain height. So if the tube is small in diameter, then the meniscus can be considered to be hemispherical. So hemispherical is like this shape over here. It's like a slight curve. So then the radius of the curvature will be given as RT is equals to RM cos 0. The cos, that one, I don't know how to, 0 is the contact angle. And we've said the contact angle ideally should be what? Should be 90 degrees. So RT is the radius of the capillary tube. RM is the radius of the curvature of the meniscus. So here is your capillary tube. RT is the radius for here. RM is the radius for this meniscus we're talking about. And this is the contact angle. Assuming it's the one that is over here. Should be 90 degrees ideally. So recalling that for curved surfaces, so there's this formula that I gave you up here, where I said the change in pressure for curved interfaces is equals to 2 surface tension over the radius. So when you recall that, in this, then for this system, it's gonna be the change in pressure is equals to 2y cos 0, which is the angle at which the capillary tube entered the liquid, over R. So this is the pressure difference between atmospheric and that immediately below the meniscus. So that's the difference between here and this one that is immediately below the meniscus. Okay, so the pressure differences between D and A causes the liquid to rise in the capillary tube until the difference is balanced by the hydrostatic pressure at the column of the liquid. So let's go back to this image. So there's gonna be a difference between this C and D, and then that's what is gonna cause the liquid to rise up here until we reach a balance. So at this equilibrium point, so remember we have this formula first, the one that we are working with, 2y cos 0 over R1. So this is equals to the height into brackets PL minus PY and by G. So H, obviously, it is the height, the height of the liquid inside the capillary tube. And then PL minus PY, that is the density difference between the liquid and its vapor, and G is the acceleration due to gravity. So given contact angles are difficult to reproduce, experiments always run at 0. That contact angle is equals to 0 or 0 to 1, achieved by careful cleaning. Hence, the equation will reduce to y is equals to RH1. This is a very long formula, but all this to say is like this formula leads to this formula, which derives this formula, which leads to this formula. Hopefully, there is no calculation in the board exam. The capillaries used must be circular in a cross section and uniform bore. So yeah, that is one of the main ways to measure surface tension. And then another one would be to use tension meters. They're also called Wilhelmy plate methods. So these apparatus, they consist of a thin mica, glass, or platinum plate attached to a suitable balance. So this is it. I think this is the balance, and then this is the thin mica. So when used as a detachment method, the plate is immersed in the liquid, and then the liquid container is gradually lowered. The reading on the balance immediately prior to the detachment is noted. So the detachment force is equal to the surface tension multiplied by the perimeter of the surface detached. That is quite a mouthful. So when using the detachment method, so the plate is gonna be immersed into the liquid. And then the liquid container is gradually lowered. Thing is though, I don't know where the plate is because I know this is the weight. Or is this the weight? I'm not sure. I'm not sure about this one, guys. I'm not very sure. In case anyone knows about it, can explain to me. Oh, I'm actually not sure. Because I'm assuming this is the plate and then this would be the balance. So when you immerse it in the liquid and then the liquid container is gradually lowered, the reading on the balance immediately prior to detachment is noted. I'm not sure about this one. Sorry. So there's the ring method. This method measures the force required to detach a platinum ring from the surface or an interface. For example, here it is. So the detachment force is equal to the surface tension multiplied by the perimeter of the liquid detached. So you just measure the force required to detach a platinum ring from a surface or the interface. So the detachment force is equal to the surface tension multiplied by the perimeter of the liquid detached. So basically you're supposed to measure the amount of liquid that is detached and then you will multiply it by the surface tension. So F is equals to 2 pi R1 plus R2 over the multiplied by the surface tension. So F is the detachment force. R1 and R2 are the inner and the outer radius of the ring. And then zero contact angle of the liquid on the ring must be assured or the equation will not hold. This can be achieved by careful cleaning and flaming of the platinum loop or by the use of a silicone treated ring for oils. Basically, you must clean it properly and make sure that the angle at which it touches the surface of the liquid is zero order. Otherwise, if it's a bit dirty, then it's gonna change the angle, and that's gonna bring a difference in your calculation. Okay. So drop weight and drop volume methods. So if the volume or weight of a drop as it is detached from a tip is of non-radius is determined, the surface or interfacial tension can be calculated using this formula. I think this is the one that we did in the lab. I'm not sure. I'm not sure if we went to the lab for this, but I think this is the one. So basically, if you know the volume or weight of a drop as it's detached from the tip, so here is the syringe, here is the drop. So if you know the weight and the volume of this drop, then you can use this methodology to calculate your surface tension. So yeah, M is the mass of the drop. V is the volume of the drop. So we said we must know the mass and the volume as well. And then P is the density of the liquid which you're measuring the surface tension. R is the radius of the tip. G is the acceleration due to gravity. And this change thing is the correction factor. So this method is easily adapted to both surface and interfacial tensions and is therefore popular. The correction factor is required as not all the drop leaves the tip of the detachment. So that means sometimes when you press the syringe, some molecules of the drop might remain. So you might have like a higher value or a lower value. That's why you need the correction factor. But also we struggled with these calculations because again, it's not a very accurate way for measuring surface tension. The correction factors are dependent. They will depend on the radius of the tip and the drop volume. it's important that the tip is completely wetted by the liquid and that the drop does not climb up outside of the tube, which means we're trying to ensure the drop doesn't go on this side, trying to be as accurate as possible. So the drop should also be formed slowly, especially in the stage immediately preceding attachment, which means when you're pushing the syringe, you have to do it slowly, you have to do it carefully to ensure like you get accurate results. Yeah. So the one thing I've not been able to explain is how you use the tension meters. But other than that, I think I am done for the first part. For the interfacial phenomenon. Any question? Any question, boys? Mko sawa? Haya, hiyo ni dozi.
Tuko sawa Saro.